ideal waveforms for dopamine. Again, I'm hoping to do some other analytes as we go on in this series, but today we're just going to look at dopamine. And there's a standard kind of waveform now for dopamine, and I'm just going to try and go over how we got there. So the first one, right, is to talk about frequency. So with the standard waveform for dopamine, we're going to do a, again, up, down, and a long hold. And this typically, maybe I should write the standard parameters just so we all know. Minus 0.4 volts is up there, 1.3 volts for the switching potential, 400 volts per second for the scan rate, and 10 hertz for the frequency, which is 100 milliseconds between scans. And so that frequency, again, we're wasting a lot of time, if you think about it. We're waiting 90 milliseconds to do a 10 millisecond experiment or so, right? That's a lot of time that we could be doing like more experiments or something. But if you do the graph here of frequency versus, I'm just going to make all of these normalized currents, so I'm going to call the top value 100, you know, kind of thing. If you do this, and we're going to say this is 10 hertz, and then we'll go all the way out to say 90 hertz is about as fast as you can go with this 10 millisecond scan kind of thing. You can't go much faster. If you've done this experiment, you know, let me do better than this. It looks something like that. I intentionally wanted to show that if this was 20 hertz, that's pretty low. And it's pretty low. I think that this is a fine shape of a curve. We're used to it. Again, there's not a particular fit to it. But I think the actual parameter you probably ought to go against would be holding time. And I've actually asked a student to do this for me one time. And so remember that the highest about holding time I'm going to do is about 90 milliseconds, and then you can get down to ones that are even like 2 or 5 milliseconds, sort of short. And then again, we're going to look at some sort of normalized I, where I'll go back to 100. And if you did that, it actually comes out pretty linear. One of the problems over here is just going from 10 to 20 hertz. This is about a 90 millisecond hold, and that one's about a 40 millisecond hold. So you lose half your holding time, right? Half the time to absorb, which is why this is the most dramatic change. And then here, again, if you actually do these out, you're changing from, oh, that was like 7 milliseconds, and that one's 5. Or, you know, so it's not that big a change, which is why it kind of bottoms out. So if you did this actually by the time you held, I think it's probably a little bit more linear. Now, this is a compromise. Could we do 5 hertz? Sure we could. And if we did 5 hertz, we'd get a point up there, right? You know, because we would have more time to absorb. There could be a time where you have maximal absorption, meaning if you fill the electrode surface, more time isn't better. I don't, in my own opinion on FSCV of dopamine, in the time scales we're at, we haven't gotten there yet. You know, so going from 10 to 5 is better, kind of thing. But this is a compromise kind of, this is the point that we like normally operate at. It's a compromise between getting enough signal that we can see things and getting enough time resolution. And so the typical things that we're looking at in the brain, you know, if this was supposed to be a, you know, a curve that we're looking at in the brain, typically these transients that we're looking at are somewhere between 2 and 5 seconds long. And so when we go at 10 hertz, we're getting 10 points per second, you know, and so we're getting a fair amount of points, if I could hit the curve, to define that curve. And so that's good. So we want to go fast enough that we can kind of define the temporal dynamics of what we're looking at, but slow enough that we actually get signal. And again, there's some special electrode designs that are going to take some of this off. But people have basically decided that 10 hertz is a pretty much good enough sampling rate for what they actually want to see in the brain. Okay, so that's the frequency. let's look at next. We'll look at holding potential. Okay, so why do we pick minus 0.4? So again, you can do an experiment where you could vary the holding potential, and I should have gone more over here, and get out a current. And if we do this again, minus 0.6 is usually about as low as we're willing to go because of oxygen reduction. I don't even like to really hold at minus 0.6, quite frankly. I think you do reduce some oxygen there, but some people do. So we'll just like randomly put in minus 0.4, minus 0.2, and then I'll go up to like plus 0.2. This graph, there's no curve or equation that defines this graph. However, as we go, it usually goes down a bit, maybe looking something like this. I wonder if I have another color that'll kind of like put that in. Yeah, something like that. So as you go more positive, you typically get a lower current. So again, strength of absorption is not necessarily a line. There's nothing that says it has to be a line. You know, you might not get that much better absorption at 0.6 than you do at 0.4. And so then again, this is a compromise. We get a lot of absorption here without actually any oxygen reduction. And so most people go there. I would like to point out that dopamine really hates a positive scan holding potential. Once you go positive on dopamine, the signal absolutely plunges. And there have been some people who have used 0. Again, I just think that's idiotic. Like, why use 0 if your instrument can go lower? Like, you don't need to hold at 0. That's not great. Holding at a positive potential is bad, but there are some other molecules that it's not as bad for, and so that's a way you can do selectivity. Dopamine doesn't like a positive. Serotonin doesn't mind it as much. Ooh, that'll give us some selectivity as we go along, as far as that goes, so to speak. All right, so number 3, we could optimize the switching potential. So this is how you know I'm a dinosaur in the field. The switching potential has changed in my career. So when I started out, the standard waveform went to 1.0 volts from minus 0.4. That is how I did my PhD thesis, was with that waveform. And so now, if you ask me what the standard waveform is, I would say, oh, I didn't draw this very well to give myself extra room. You know, almost everybody goes up to 1.3 volts now instead of 1.0 volt. And you say, what happened? I think a couple things happened. Number one, the amplifier might have been limited to 1.0 back in the day. If you think about putting things on like a 10-volt scale, 1.0 goes really nicely. And in fact, when we've looked at buying some other equipment, sometimes we're like, that's fine, but I can't get you over 1 volt. And now I'm like, don't want any potentiostat that doesn't get me over 1 volt. You know, but back in the day, I think the potentiostats were a little bit limiting, you know, to 1.0 volts. But there's an inherent thing of like, why go higher? It shouldn't theoretically matter. So I want to get that in your brain first before I tell you why it does matter. It should not matter. If I am doing FSCV and I am like doing my thing, I'm going to mark 1.0 volts here. I am done with my peak. If I am done with my peak, why am I wasting my time going out to 1.3 to come back, oops, you know, to come back and then, you know, do my reduction? If I have oxidized everything that's on the surface before that point, I'm done, right? And so if you look at your cyclovoltammogram, you're done by 1.0 volts. Like, why would you go higher? Theoretically, it shouldn't matter. Like, you should not get more electrochemistry. You've done your electrochemistry. So I'd like to point out, if you read the textbook, it would tell you it wouldn't matter. There's a problem. It does matter on carbon electrodes, right? So it's not a fact of electrochemistry. Electrochemistry is done. It's a fact of a carbon electrode. So with my carbon electrode, right, I have a carbon electrode surface. I don't even know how to draw that very well. And on that surface, we have, you know, typically, you know, lots of kind of benzene rings, and they're going to end, oh gosh, I'm going to draw this terribly. On the edge, we get these things that we are going to call an edge plane. And then this is what we call a basal plane. And on the edge, we'll often be able, there'll be like defect sites, right? Well, that'll be hanging and maybe a radical or something like that. So we'll get defects in the surface that are, you know, not perfect kind of graphene. We'll also get sometimes some, you know, surface groups, that kind of thing, that we've oxidized the surface. So on this, we kind of have a surface. So it turns out that when we go, Whiteman had a really great paper about this, when we go at about 1.3 volts or greater, we end up having enough energy to break carbon-carbon bonds on this surface. So I have an energy to break a bond there. And so by breaking that bond, well, that makes no sense, it's not hanging carbon. When I break a bond, I'm creating defect sites. And again, a lot of these defect sites might eventually react with oxygen in the air or whatever and become oxygen functional groups. So I am changing the surface of the electrode when I go to a higher voltage than 1.3 volts, as I said. The textbook says it shouldn't matter. You got all the energy you need. More isn't going to help you. It does matter. If you do the graph, the graph on this typically looks something like this, 1.0 volts. Again, it's very electrode dependent, but oftentimes the points will kind of be a little bit low and then it'll jump up a little bit more with the higher ones. That's a very approximate graph. I feel like it's very electrode dependent. Again, there's no equation. That's not a line. It's no equation that tells you what it should look like. It's more of a jump of, oh, did you get enough voltage to be able to fundamentally change the surface? This is also why I always tell people electrodes have memories. If you've ever gone to a high voltage, you've activated the surface. You can't go back to 1.0. So if you were doing this experiment over here, and you start low and you go high, and maybe you get these kind of brown points that I'm trying to make look bigger here. But if you were to go back down now from this, you know, okay, that would be the same. You know, you might get points that look like that. They don't go back down to the original values they started at. Same thing with scan rate. You can't screaming fast scan rate, it activates the surface, only to go back down where the surface does not look the same. So these experiments are directional because your electrode remembers that it has an activated surface. Once you activate a surface, you can't go back. So now almost everybody likes to act at this activated surface. It helps with fouling. It helps with kind of renewing the surface and that kind of thing. Theoretically, Whiteman did this where he did this like this electrode, this potential is for like 2 days or 3 days, and then like the diameter decreased by half. Because you just keep breaking carbon bonds and you break off little bits of carbon, that kind of thing. So it's kind of amazing that you can break off the surface. So this is really special about carbon electrodes, and so we're going to exploit this a lot, you know, in carbon electrode kind of development in FSCV. But again, it's one of those kind of things that was discovered to be a special property of carbon electrodes. All right, last thing on the ideal waveform is scan rate. What goes into scan rate? Oh, I erased my waveform. That's okay. We know what it looks like by now. And so a lot goes into scan rate. So for absorption-controlled reactions, your Faraday current is proportional to scan rate. This is just scan rate. That's little v. So any, you know, one saying that, so, oh, I want to scan fast, right? I'll get big currents. Unfortunately, your kind of background is also proportional to scan rate. And the higher your background current, that means the noise also increases with scan rate. So it's a little hard to just make the argument, go fast, go fast, go fast, because you'll get bigger currents. It's like, yeah, you'll get bigger currents all around, which means you'll also get bigger noise. And what really matters in analytical chemistry is signal noise. Right, so you don't just win on signal, sadly. By the way, there's like a 1980s Steve Weber paper that talks about this, and it's like the only place I ever found where they actually like do the theory on why the noise goes up with the background current going up too. I cite that paper a lot. Okay, so that's true. So because of this, though, I is proportional to scan rate. If we were to do the experiment, again, where we were to vary the scan rate in volts per second, and we'll get some sort of normalized current, again, you should get a line, right? Where these points would fall on a line, and any good electrochemist in the vent lab at least probably has done this experiment and been expected to get a line. It just shows that you're really careful in your experimental things. It really does work. So yeah, you should get a line. Now we're limited down here. About the lowest scan rate you can go is about 50 volts per second, or else that 10 hertz is messed up. If you can't have a scan that takes more than 100 milliseconds. So you're limited on the low side, or else you're going to be changing that. And on the high side, the question is what's limiting. Practically, people don't typically go much over 1,000. You could go maybe 2,000, something like that, as far as that goes. More practically, it's actually better to take and do a log plot. Maybe we do natural log. I don't think it matters. We're going to do a log plot here. And if you do the log plot, again, for something that's absorption controlled, it should come out with a slope equal to 1. But if you were to do something diffusion controlled, then you should end up with a slope of 0.5, right? Because that goes with the square root of scan rate. And then practically sometimes you get in the middle. That's 0.75 slope. Great, we have kind of a mixture of absorption and diffusion control. But this is a little bit better than just like, oh, does that really fit a line? What's this 0.97 good enough? How about 0.96? Yeah, whatever, R squared. This will give you a more practical thing of whether or not you're doing this experiment correctly. As I mentioned before, the other thing about scan rate is that, you know, if you go really slowly, your peaks will be close together, and the faster you go, the more they move out. And so there's practical kind of limits. If we go super fast, we only have a working range of about minus 0.5 to 1.5. That it makes it hard to see your electrodes, particularly if you're looking at things that have a higher oxidation potential. Dopamine, we've got room. As I said, we've got room to move it out. Something like adenosine or histamine or hydrogen peroxide, things that occur more at 1.5. If you don't spend enough time there, you just don't get enough absorption. And so we'll talk about that. I also believe from my practical experience that in vivo, I've seen a lot less stability with waveforms that we tried to go at like 1,000 volts per second. I don't know if it causes the neurons to fire or what's happening there, but it just isn't my favorite to go much more than 400 or 500, 600 volts. The serotonin waveform's the exception. That one seems to be fine and stable at 1,000 volts per second. But practically, you know, again, 400 volts per second is probably somewhere down here on my, you know, thing, and you're like, well, that you're not maximizing. No, we're not maximizing, but it's good enough. It gives us pretty stable signals in vivo. Again, it's sort of funny. It used to be 300 when they got a little bit better amplifiers, et cetera. They sneaked it up to 400. The practical difference probably isn't real large. Okay, so that was waveforms and shape. I'm going to just do one quick last thing, and that is that the CV is not the end-all be-all in FSCV. So we don't just collect one CV, although we've spent a heck of a lot of time just looking at one CV, right? We're going to do this again and again and again, and so we collect a lot of data points. And so one way that we do look at them are current versus time plots, or we call these I versus T plots. And so you imagine, again, you take a CV, and then you take another CV. I'm going to intentionally try to make it smaller. I don't know. And then you take another CV, you know. And then what we can do is plot these peak things over time. And if I did that for these random CVs I just write, you know, over time, I would get something that looks like that, right? So what we normally do in our experiments, let's say we're doing a flow cell experiment where we inject a plug of dopamine. Typically we're going to get nothing, and then it's going to go up, and like kind of look like this, and then it's going to come back down, and it often doesn't come back down to baseline. I drew a baseline there on purpose. I drew that in points on purpose because this is a sampling. I'm taking a point every 100 milliseconds, right? This is 10 hertz sampling. Now, practically, what do? Yeah, we draw a line through it, you know, kind of thing. All right, yeah, so we draw a line. It's easier to connect the points to the line. But I want you to see that practically, this is not a continuous something. This is, you know, sampled. So we get an I versus T, and it looks something like this. If you wanted to, you could calculate a rise time. So usually we calculate rise time as the 10 to 90%, so from 10% to 90%. That eliminates you having to figure out the peak. And if you did that, again, I would argue for dopamine and a carbon fiber microelectrode, I would say the rise time is on the order of probably about 1 second. Something like that. Maybe a little less, you know, maybe half a second, something like that. So how long does it take to go up? On this, you'll notice we get kind of, it's a little bit slow. Ideally, in an ideal situation, if we had the ideal flow cell, this would inject a box, right? And so it should look like a box. And it does not look like a box. And so all of these deviations where it's a little slow and kind of reaching the peak, and then it's a little slow, that box should have come down before that. It should be a little slow. Box. This marker isn't very good. Anyways, my box should come down before that. A little bit slow. These deviations, again, if you haven't learned the name of the game, blame everything on absorption. But that's the problem. We're waiting for it to absorb, so we don't quite have the full surface, you know, that kind of thing. And here it hangs up because you still have some absorbed DA that's left on the surface, right? So it hasn't all fallen off. So even though I've injected, my injection's done, like this is in like a flow cell, some of it's hung on and it often doesn't quite go down to baseline. These are very helpful though. We use these all the time because this is just the way, you want to know how something changes over time, how dopamine changes over time in your brain. You don't want to look at 2,000 CVs or, you know, 200 CVs. That's 20 seconds worth of data is 200 CVs, right? You know, you don't want to look at 200 CVs. You don't, you know, a lot of other data analysis things put out a line plot, fluorescence, so this is how the fluorescence went up. You know, amperometry would put out a line plot, you know, et cetera, et cetera. So people are used to looking at line plots of how things change. But in the FSCV world, this is where my drawing skills are really going to be hampered, partially because I did not write a green. We are like, oh, but line plots still don't show all of our data, right? We would rather do a color plot. And so on our color plot, if I brought green, that would be it. I didn't bring green. My blue is rapidly running out. This should be blue up there. And that's what the typical color plot looks like for dopamine. So let's just quickly go over what we're looking at for a color plot. So this is the start on the left-hand side of the voltage. We're ramping up to 1.3, so this would be the middle. And then this is the down, so this is the up. And this is the down back to minus 0.4. There's a kind of a browny yellow color that represents 0. And then, again, green is the highest for the oxidation, and blue is what it looks like for reduction. These colors were designed by Mark Whiteman, who is colorblind, and he said he could actually see them. And so there's a lot of other colors he could not see. You know, so whether he could see true green and true blue, I don't know, but he could see the difference in the colors. So this then is time on the x-axis, and then current intensity, if I had a real color plot, right? And so we usually have a scale where we have some sort of green up here, and that's our most intense oxidation. We have blue down here, that's our most intense reduction. And again, somewhere in the middle it's brown, and that's 0. One thing to notice, I told you the oxidation is always bigger than the reduction. These plots are standard so that this is in a 3:2 ratio. If you put this plot in a different ratio, you get different colors, and they don't look right. So if this is, you know, 6, that needs to be 4, that kind of thing. Our programs are good about automatically doing that, but if you start to fuss with it, you could get it out of ratio, and if it's out of ratio, it will not look right, kind of thing. So again, this is basically, you know, every one of these is kind of like a CV. Now I'm going to really challenge myself to draw a CV kind of this way. So you know, you have your kind of oxidation peak and then your reduction peak, right? And so we have one of these, and we have these CV, 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 right? And where these then are going to be color-coded, you know, for green as they go along, and then these reduction peaks are color-coded blue. Get a lot of extra peaks in there. Again, some of those are background subtraction errors. If the background changes at all, that'll give you a color. Some of that can be ionic changes. Ions, like changing the background again, will give it to you. Sometimes there may be other things that are happening. And so again, our lab developed a computer program to do color plot analysis. And I might talk about it more when I talk about adenosine in the next lecture. But that, you know, there are some idiosyncrasies of color plots, and it's like looking at an image, looking at all the data. We think that using color plots will be able to tell things apart better than just using a simple CV at one given point in time, or a simple I versus T at one point in time. And so again, FSCV people love their color plots because you can look at all the data. We often simplify it to line plots if we just want to talk about what's happening at one point in the brain, and then we study CVs to really learn the fundamentals, which is why that's where I started.